Hello and welcome to the Big Bang. Today, I want to talk about how probability revolves around functions. So, whenever we talk about functions, sometimes the phrases black box or mapping come up. So why are we talking about functions in a probability course? Probability might not seem like a function because we do not have a math equation for it, like f of x is equal to x plus 2. Or do we? The black box means that we can put in an input, something happens inside of the black box, and we get an output based on what went on in the black box. So if f of x is equal to x plus 2, then we can predictably put in 2 and get out 4. Well, what if we could get that same power of prediction in probability? Probability theory allows you to glimpse inside of the black box. Once something is a function, we know how to deal with it. It turns out, when you conduct a random experiment, you're creating a large box. This large box contains all of the possible outcomes from that random experiment. We call this the sample space. But we often do not want to look at such large amounts of data, so we take a subset of that sample space. For example, our sample space could be a series of coin tosses. Our subset, or event, could be 3 coin tosses in a row. We can get 8 different combinations: HHH, HHT, HTT, TTT, TTH, THT, THH, and HTH. Ooh, that's a mouthful. Right now, the example is simple enough to write out all of the possibilities. But what if we wanted to look at 5 coin tosses in a row, or 20, or 200? Wouldn't it just be easier just to quantify something? So let's look at the number of heads in 3 coin tosses. Now, let's input that list from before and see what we get. When we take out the repeating numbers, all we have left is the set 0, 1, 2, 3. Isn't that easier to look at and keep track of? What you just saw is exactly what a random variable does. The input is the qualitative event and the output is a quantity. A random variable is a function, and that's because it maps from the sample space to the real number line. So, why are random variables, otherwise known as RVs, important? Once we have numeric values, we can more easily analyze and visualize a subset of the original sample space. This comes from the random experiment, which we perform to try to predict the outcomes. Here are where probability distributions, PMF, PDF, and CDF come into play. Numbers also allow us to name subsets with more convenience. We know probability is a function of a subset of the sample space. Let's take the event of rolling a 6-sided die. We could say that the probability of the event of the roll being even, or we could say the probability of the set 2, 4, 6. So the argument of the probability function is a random variable taking on a certain value. Remember, a random variable is a function, so probability is also a function. Here are 2 more key notes to write down. Probability mass functions, otherwise known as PMF, have units of probability, but probability density functions, they're not actually probabilities. PDFs have units of probability per unit length. That's why you must integrate PDFs to find the probability. Think about how velocity has units of meters per second. When you integrate a velocity function, you get a position function, which has units of just meters. The same concept applies to getting probability from PDFs. Expectation is a nice linear operator, but variance is a quadratic operator. Variance involves the expectation of a square. That's why variance is often written as sigma squared. If you do not completely understand everything right now, that's okay. Just refer back to this video throughout the course to see if you can start to understand why probability is a function, and many formulas are functions of functions. Good luck, and I'll see you in the next video.